Across the quiet background of an expanding universe, our entire Milky Way is not standing still. Measurements show it moving at more than 1.3 million miles per hour, about 370 miles per second, roughly 600 kilometers per second. That motion is steady, directional, and shared by many neighboring galaxies. Expansion alone cannot explain it. Something immense is shaping this flow, exerting influence across hundreds of millions of light-years. Tonight we examine how astronomers uncovered this hidden pull step by measured step, using real data, careful surveys, and decades of observation. We begin with Part 1. Why is the Milky Way moving at over 1.3 million miles per hour through space, where the first precise measurements revealed that our galaxy is already in motion? If the universe is expanding smoothly in every direction, why does our entire Milky Way appear to be moving through space at nearly 600 kilometers per second, a speed that is not random, not local, and not easily explained? This motion is not inferred from a single galaxy or a rough estimate. It is measured, confirmed, and repeated across decades of observation, and it immediately breaks a comforting assumption that on the largest scales everything is simply drifting apart evenly. The first firm clue arrived in the 1960s, not from galaxies themselves, but from radiation. In 1965, Arno Penzias and Robert Wilson, working with a Bell Labs horn antenna originally built for satellite communication, detected a persistent microwave signal coming from every direction in the sky. This signal, later identified as the cosmic microwave background, was quickly understood as relic radiation from the early universe released when matter and light first decoupled roughly 38,000 years after the Big Bang. At first glance, this background appeared almost perfectly uniform, with a temperature close to 2.7 Kelvin. Almost, but not quite. When scientists began measuring the microwave background with higher precision, they noticed a subtle pattern. One side of the sky appeared slightly warmer, the opposite side slightly cooler. The difference was tiny, about 0.003 of a Kelvin, but consistent. This pattern, now known as the cosmic microwave background dipole, had a straightforward physical interpretation. If an observer is moving relative to the background radiation, the radiation in the direction of motion appears slightly blue-shifted, while radiation behind appears red-shifted. The dipole was not noise. It was a velocity signature. By the late 1960s and early 1970s, researchers concluded that the solar system is moving relative to the cosmic microwave background at roughly 370 kilometers per second. Later refinements showed that this motion is not just local to the Sun or even to the Milky Way's disk. The entire local group of galaxies, including Andromeda and dozens of smaller companions, shares nearly the same velocity vector. That realization carried weight. Local gravitational interactions between the Milky Way and Andromeda, for example, cannot account for a shared motion on this scale. As measurements improved with satellites such as COBE in the 1990s, followed by WMAP and later Planck, the dipole signal became one of the most precisely measured features in all of cosmology. Planck's final data release constrained our velocity relative to the cosmic microwave background to about 369 kilometers per second, with uncertainties of less than 1 kilometer per second. This is not an estimate drifting with theory. It is an empirical number anchored in observation. At this point, a deeper issue surfaced. The expansion of the universe, first identified by Edwin Hubble in the 1920s, describes how distant galaxies recede from one another on average. That expansion does not pick a direction. It stretches space itself. The dipole motion, however, does pick a direction. It implies a peculiar velocity, a motion on top of expansion, driven by gravity rather than cosmology alone. Astronomers began to look for corroborating evidence in galaxy surveys. Redshift data from thousands of galaxies revealed that this motion is not unique to the Milky Way. Nearby galaxy clusters also exhibit similar directional drift. The Virgo cluster, for example, shows evidence of motion aligned with the same general flow. Even larger structures, collections of clusters, appear to share components of this velocity. These observations suggested that something on scales far larger than individual galaxies must be exerting influence. Gravity remains the only known interaction capable of shaping motion on such enormous distances. Electromagnetic forces cancel out at large scales. Nuclear forces are confined to subatomic ranges. Only gravity, cumulative and long-ranged, can coordinate the movement of systems separated by tens or hundreds of millions of light-years. This immediately raises a demanding constraint. Whatever is responsible must contain a tremendous amount of mass. In the early days, astronomers attempted to explain the motion using visible matter alone. Known clusters and superclusters were catalogued their masses, estimated from galaxy velocities and X-ray emissions of hot intracluster gas. These calculations fell short. The visible mass did not provide enough gravitational pull to account for the measured velocities. The discrepancy echoed a familiar problem already well known from galaxy rotation curves studied by Vera Rubin and others. Once again, mass inferred from motion exceeded mass seen in light. By the 1970s, redshift surveys began mapping galaxies in 3 dimensions more systematically. These surveys revealed that galaxies are not distributed randomly. They form walls, filaments, and dense knots separated by large voids. Motion appeared to flow along these structures. Certain regions behaved as gravitational basins, drawing matter inward over enormous distances. One such region lay in a particularly inconvenient direction. When astronomers traced the vector of our motion backward, it pointed toward a region of the sky heavily obscured by the Milky Way's own dust and stars. Optical telescopes could not see through it. This area became known as the zone of avoidance, not because nothing existed there, but because observation was blocked. The implication was unsettling. The source of the pull shaping our galaxy's motion might be hidden directly behind our own. Edwin Hubble himself had warned earlier that motion carries information about structure. He wrote that motion reveals structure, a statement that would gain new relevance decades later. Here, motion was revealing something massive enough to influence entire clusters, yet elusive enough to remain poorly characterized. As radio and infrared astronomy improved, particularly in the late 20th century, astronomers began peering through the zone of avoidance. They detected previously unknown galaxies and clusters. Still, even these discoveries accounted for only part of the observed flow. The scale of the motion suggested not a single galaxy or cluster, but a vast region of enhanced mass density, a gravitational feature rather than a discrete object. This realization marked a shift. The problem was no longer framed as identifying a lone cosmic body. Instead, it became a question of mapping large-scale mass distribution. How uneven is matter on the largest scales? How far do gravitational influences extend before cosmic expansion dominates completely? These questions were not abstract. They were anchored in data, measured velocities, mapped redshifts, and the precise anisotropy of the cosmic microwave background. The measured speed of our galaxy, over 1 million kilometers per hour, is modest compared to speeds near black holes, but extraordinary in a cosmological context. It reflects motion accumulated over billions of years under persistent gravitational influence. At this scale, even a slight imbalance in mass distribution can produce sustained acceleration. Importantly, none of this implies danger or instability. These motions unfold over timescales far longer than the lifetime of stars or planetary systems. The Milky Way is not being yanked suddenly through space. It is responding gradually to the deep structure of the universe. What makes this discovery enduring is not its drama, but its restraint. The numbers are small, the signals subtle, the conclusions cautious. Yet, taken together, They point toward a consistent picture: our galaxy is embedded in a flow shaped by structures far beyond its own boundaries. Structures that were invisible at first, not because they were exotic, but because our instruments were incomplete. The dipole in the cosmic microwave background does not explain what is pulling us. It does something more fundamental. It establishes that we are moving, and that the motion is real, shared, and directional. From that single, precise measurement, an entire line of investigation follows, one that challenges the assumption that light alone reveals mass. As observational tools improved and surveys expanded, the evidence accumulated quietly. Galaxy velocities aligned, cluster motions correlated, mass estimates diverged from luminosity. Each result reinforced the same conclusion without stating it outright. Something large, extended, and largely unseen was shaping the trajectory of our cosmic neighborhood. That understanding brings us naturally forward. Once motion is present, attention turns to something deeper. What kind of force can sustain it? And how gravity continues to shape structure, even across distances that once seemed far beyond its reach. Part 2. What force is strong enough to drag thousands of galaxies together? If gravity weakens with distance and cosmic expansion stretches space itself, how can thousands of galaxies still move together across spans exceeding 150 million light-years, roughly 46 megaparsecs, without drifting apart? The question cuts directly into the mechanics of the universe, because it challenges a simple picture in which expansion always wins once distances become large enough. The first step toward answering this did not come from theory, but from careful measurement. Astronomers learned early that a galaxy's observed redshift contains two ingredients. One comes from cosmic expansion, the gradual increase in distance as space itself grows. The other comes from local motion, the galaxy's own travel through space under the influence of gravity. This second component became known as peculiar velocity. It is not peculiar because it is strange, but because it is peculiar to the object separate from the overall expansion. Measuring peculiar velocity is difficult. It requires knowing not just how fast a galaxy appears to recede, but how far away it truly is. In the 1970s and 1980s, astronomers developed distance indicators that allowed this separation. Spiral galaxies, for example, obey the Tully-Fisher relation, linking their rotation speed to their intrinsic brightness. Elliptical galaxies follow similar relations, connecting stellar motion to luminosity. By comparing intrinsic brightness with observed brightness, astronomers could estimate distance, subtract the expansion component, and isolate the galaxy's own motion. When these methods were applied to large samples, a pattern emerged. Galaxies were not moving randomly. Entire groups and clusters shared similar peculiar velocities. The Virgo cluster, the Hydra Centaurus region, and other massive structures showed coherent motion in the same general direction. This was not a statistical fluke. Independent surveys using different techniques and instruments reached the same conclusion. The implication was immediate and demanding. A single galaxy cannot pull an entire cluster. Even a cluster cannot easily influence others tens of megaparsecs away. To produce coherent motion across such scales, gravity must arise from a vast concentration of mass distributed over a region far larger than any one visible object. At this point, astronomers faced a balancing act between two well-tested ideas. On one side stood cosmic expansion, measured precisely through redshift surveys and confirmed by observations of distant supernovae and the cosmic microwave background. On the other stood gravity, known to dominate structure formation at smaller scales. The observed flows suggested that locally gravity could still overcome expansion provided enough mass was present. The numbers clarify this balance. Expansion increases relative velocities between distant objects by roughly 70 kilometers per second per megaparsec in the present universe. Over 46 megaparsecs, that amounts to several thousand kilometers per second. To counteract this, gravity must come from a mass concentration on the order of 10 to the power of 16 times the mass of the Sun, spread across a broad region. This is not the mass of a galaxy. It is the mass of a supercluster-scale structure. X-ray astronomy offered an independent line of evidence. Observations from satellites operated by NASA and the European Space Agency revealed enormous reservoirs of hot gas trapped in galaxy clusters. This gas, heated to tens of millions of Kelvin, emits X-rays and responds directly to the cluster's gravitational potential. By measuring gas temperature and distribution, astronomers could estimate total mass. Again, the result was consistent. The gravitational pull, inferred from gas motion, exceeded what visible galaxies alone could provide. This was not a new problem. Vera Rubin's work on galaxy rotation curves had already shown that stars orbit faster than visible mass allows. On cluster scales, Fritz Zwicky had noticed a similar discrepancy decades earlier when studying the Coma cluster. What was new here was scale and coherence. The same mismatch appeared not just within galaxies or clusters, but across entire regions containing thousands of galaxies moving together. As more data accumulated, astronomers began mapping cosmic flows directly. Instead of focusing on where galaxies are, they examined how galaxies move. Velocity maps revealed streams, convergences, and broad basins where motion slowed and turned inward. These basins were gravitational features, not points. Matter flowed toward them much like air flows toward a low-pressure region in the atmosphere, except the timescales were measured in billions of years. NASA-supported surveys such as the Cosmic Flows projects refined these maps. They combined distance indicators from thousands of galaxies to reconstruct three-dimensional velocity fields. The result was striking. Our local region of the universe is not drifting aimlessly. It is part of a larger flow directed toward a dense region hidden partly behind the Milky Way. This finding carried an important constraint. The force involved cannot be transient. Short-lived events, such as galaxy collisions or explosions, do not produce sustained motion over hundreds of millions of light-years. The pull must come from long-lived mass concentrations that formed early and persisted as structure grew. This points directly to the role of dark matter, which dominates mass on large scales and clumps into filaments and nodes that shape cosmic architecture. Computer simulations strengthened this interpretation. Large-scale structure simulations, run on supercomputers and calibrated using cosmic microwave background data from Planck, reproduce similar flows only when dark matter is included. Without it, matter remains too diffuse. With it, gravity organizes matter into filaments and basins that guide motion across vast distances. Carl Sagan once remarked that the universe is a very big place, perhaps the biggest, and on these scales size alone becomes a physical parameter. Gravity does not need to be strong at any single point. It needs only to be persistent, cumulative, and unevenly distributed. Over cosmic time, even small imbalances in mass density grow into dominant features that steer motion. What makes this discovery compelling is how indirect it is. No telescope image shows a hand pulling galaxies together. Instead, motion itself becomes the evidence. Velocities align, directions converge. The pattern repeats across independent data sets. Each measurement is modest on its own. Together, they form a consistent picture that resists simpler explanations. It is important to note what this does not imply. Galaxies are not being torn apart. Clusters are not collapsing catastrophically. Expansion still governs the universe at the largest scales. But within certain regions, gravity remains strong enough to slow expansion, redirect motion, and create long-lived flows. By the end of this line of investigation, astronomers were forced to revise a quiet assumption. The universe does not expand uniformly everywhere when examined closely. On intermediate scales, structure matters, mass matters, Motion traces the invisible scaffolding of matter that light alone cannot reveal. The force dragging thousands of galaxies together is not exotic. It is gravity, operating exactly as described by general relativity, but amplified by scale accumulation and unseen mass. What remains uncertain is not the existence of the pull, but the detailed shape and extent of the basin creating it. As velocity maps became more precise, one detail grew harder to set aside. The motion did not settle toward a single cluster or supercluster that could be cleanly identified. Instead, it leaned toward a wider region, partly concealed, whose overall structure was still uncertain. What stood out was that this direction was traced through motion rather than light, carrying the discussion forward to a point where astronomers had to consider how a massive influence might be inferred even when its source could not yet be clearly seen. Part 3. Did astronomers accidentally discover an invisible monster in the 1970s? What does it mean when galaxies move as if something enormous exists, even though telescopes reveal almost nothing in that direction? 1970s. This question emerged quietly from stacks of numerical tables, long nights of data reduction, and a growing unease among astronomers who were accustomed to trusting light as the final authority. By that decade, redshift surveys had become a primary tool for understanding the large-scale universe. Using optical telescopes, astronomers measured how much a galaxy's spectral lines were shifted toward longer wavelengths, a direct indicator of its recessional velocity. When combined with distance estimates, these redshifts allowed researchers to reconstruct the three-dimensional distribution of galaxies. The expectation was straightforward. Matter traced by light would explain motion traced by velocity. What appeared instead was a pattern that refused to align with that assumption. As surveys expanded beyond the local group, astronomers noticed that galaxies across a wide region of sky were not behaving independently. Their redshifts showed systematic deviations from what cosmic expansion alone would predict. These deviations were not random scatter. They were aligned, coherent, and directional. Entire clusters were drifting together, as though responding to a shared influence. At first, the anomaly was subtle. Individual measurements could be dismissed as uncertainties in distance estimates, but as data accumulated, the signal strengthened. The effect persisted across different observing programs, different telescopes, and different teams. Something was shaping motion on scales far exceeding any known galaxy cluster. The difficulty lay not in measuring the motion, but in identifying its source. When astronomers pointed their telescopes along the inferred direction of the flow, they saw very little. Optical images showed sparse galaxies, interrupted by dense fields of Milky Way stars and dust. This region of sky fell near the plane of our own galaxy, where interstellar dust absorbs visible light. To optical surveys, it appeared almost empty. This mismatch created a tension that could not be resolved by calibration alone. If gravity was responsible for the observed velocities, then mass must be present. If mass was present, it should leave some trace in light. Yet light was largely absent. In the mid-1970s, researchers began to consider a possibility that felt deeply uncomfortable at the time. Perhaps the relationship between light and mass was not as reliable as assumed. Fritz Zwicky had raised this concern decades earlier, when studying galaxy clusters, and Vera Rubin had reinforced it through galaxy rotation curves. But now the same issue was appearing at an even larger scale. Redshift surveys, conducted by astronomers such as Alan Dressler and collaborators, revealed a region toward the constellations of Centaurus and Norma, where galaxy motions converged. This convergence implied a massive gravitational influence, yet optical catalogues showed no single structure capable of accounting for it. The region behaved as though dominated by a vast concentration of matter that telescopes could not clearly see. By the late 1970s, the term Great Attractor began to circulate informally among astronomers. It was not introduced as a claim, but as a placeholder, a name for an influence, inferred from motion, not from direct imaging. The phrase captured both scale and uncertainty. Great because the mass required was enormous. Attractor because gravity was the only viable explanation. The story behind this naming is telling. Astronomers did not set out to find a hidden structure. They were attempting to map galaxy distributions and velocities. The Great Attractor emerged as a byproduct of that effort, an inference drawn reluctantly from consistent data. It was an accidental discovery in the strictest sense, arising not from a targeted search, but from the refusal of observations to fit existing expectations. Skepticism followed naturally. Could distance indicators be biased? Could selection effects distort the apparent flow? Teams revisited their methods, recalibrated relations, and compared independent samples. The anomaly remained. When infrared observations were introduced capable of seeing through dust more effectively than visible light, they began to reveal previously hidden galaxies in the same region. Still, even these discoveries accounted for only part of the gravitational pull. Radio astronomy added another piece. Neutral hydrogen emits radiation at a wavelength of 21 centimeters, which passes through dust largely unaffected. Surveys using this emission detected galaxies invisible in optical light. These galaxies clustered in the same general direction, indicated by velocity flows. The evidence began to converge not toward a single object, but toward a dense region embedded within the cosmic web. The unsettling aspect of this realization was not the existence of unseen matter. That idea was already gaining acceptance. It was the scale. The inferred mass exceeded the Milky Way by tens of thousands of times. Even combined visible galaxies could not account for it. Dark matter distributed unevenly appeared to dominate the gravitational landscape. NASA and European Space Agency observations of X-ray emitting gas further reinforced this picture. Clusters near the inferred location of the Great Attractor contained vast amounts of hot gas bound tightly by gravity. The temperature and motion of this gas implied deep gravitational wells. These wells aligned with the direction of the observed cosmic flow. At no point did astronomers claim to have seen the Great Attractor directly. What they had seen was its effect. This distinction mattered. The scientific caution surrounding the term reflected an awareness that inference must remain separate from observation. Yet inference, when supported by multiple independent lines of evidence, carries weight. Carl Sagan once emphasized that extraordinary claims require extraordinary evidence. In this case, the claim was not extraordinary in nature, but in implication. It suggested that the largest motions of galaxies were governed by structures only partially visible, and that light alone offered an incomplete map of reality. The evidence supporting this view came not from a single dramatic image, but from the quiet agreement of velocities measured across the sky. As the 1970s gave way to the 1980s, the Great Attractor shifted from curiosity to working hypothesis. It shaped how astronomers designed surveys and motivated the development of multi-wavelength astronomy. If visible light could not reveal mass reliably, then infrared radio and X-ray observations would be necessary to complete the picture. The broader consequence of this episode was a change in perspective. Redshift surveys were no longer interpreted solely as maps of where galaxies are. They became maps of how gravity sculpts motion. In this framework, empty-looking regions could still exert profound influence, and crowded regions might not dominate dynamics as expected. Importantly, the Great Attractor was never framed as a final answer. It was recognized as an approximation, a label applied to a gravitational basin whose full extent was unknown. Subsequent work would show that it is part of a larger network of mass concentrations rather than an isolated entity. Yet the lesson of the 1970s remains. Astronomers did not discover an invisible monster by looking for one. They discovered it by paying attention to motion, by trusting carefully measured velocities, even when images offered little reassurance. In doing so, they uncovered a fundamental truth about the universe. Structure is not always where light is brightest. Sometimes it is where motion insists it must be. That focus does not stop here. As observations extend into regions thick with obscuring material and surveys broaden their coverage, the Great Attractor appears less like a single anomaly and more like an entry point into how mass arranges the universe beyond what direct light can reveal. Once such an unseen influence is recognized, attention shifts to a quieter complication: why it stayed concealed for so long, and how the structure of our own galaxy interferes with our ability to view it directly. Part 4. Why is the most powerful gravitational region hidden behind our own galaxy? What if the region shaping the motion of our galaxy lies almost exactly in the one direction where our telescopes struggle the most, buried behind the dense dust and stars of the Milky Way itself? This is not a coincidence designed for mystery. It is a consequence of where we observe from and of how matter inside our own galaxy interferes with our view of the wider universe. From Earth, the Milky Way appears as a bright band stretching across the sky. To the naked eye, it is a beautiful concentration of stars. To astronomers attempting to map the universe beyond it is also an obstacle. The disk of our galaxy contains vast amounts of interstellar dust, gas, and crowded stellar fields. This material absorbs and scatters visible light. Galaxies lying behind it are not absent. Their light is simply blocked before it reaches us. This obstruction is known as the zone of avoidance. The term does not imply emptiness. It reflects a limitation of observation. In visible light surveys, roughly 20% of the extragalactic sky is severely obscured by the Milky Way. Early galaxy catalogs simply avoided these regions because reliable measurements were impossible. For decades, large-scale maps of the universe contained a conspicuous gap precisely where the inferred direction of cosmic flow pointed. The implications became serious once velocity measurements indicated that the gravitational pull influencing our local group and neighboring clusters originated from within this obscured band. Astronomers were forced to confront an uncomfortable reality. The strongest nearby gravitational influence might lie in the very direction where standard observational tools performed the worst. Understanding why this happens requires a brief look at the physical properties of interstellar dust. Dust grains are tiny, often smaller than a micrometer, but they are efficient at blocking visible light. They absorb short wavelengths and scatter them out of the line of sight. Over distances of thousands of light-years within the Milky Way's disk, this effect compounds. Entire galaxies beyond the disk can be dimmed by factors of hundreds or more, rendering them effectively invisible in optical surveys. This limitation shaped early cosmology. When Edwin Hubble and his contemporaries mapped the distribution of galaxies, they relied almost entirely on visible light. Their maps showed a universe structured into clusters and voids, but with a conspicuous absence along the galactic plane. At the time, this absence was treated as an observational inconvenience rather than a physical concern. Motion studies later forced a reassessment. Once astronomers realized that galaxy velocities pointed toward the zone of avoidance, new strategies became necessary. If visible light could not penetrate the dust, other wavelengths might. The first major breakthrough came from radio astronomy. Neutral hydrogen emits radiation at a wavelength of 21 centimeters, which passes through interstellar dust with little attenuation. Surveys using radio telescopes began detecting galaxies hidden behind the Milky Way, revealing that the zone of avoidance was far from empty. These radio surveys uncovered spiral galaxies with significant mass previously unaccounted for in gravitational analyses. Some were part of clusters that extended across the galactic plane. Others appeared as isolated systems, contributing incrementally to the total mass budget. While these discoveries did not immediately explain the full gravitational pull inferred from velocity flows, they narrowed the gap between observation and inference. Infrared astronomy provided the next layer of clarity. Infrared light has longer wavelengths than visible light and is less affected by dust. Missions supported by NASA and the European Space Agency, such as the Infrared Astronomical Satellite, and later, the Wide-Field Infrared Survey Explorer, scanned the sky in infrared bands. These surveys revealed dense concentrations of galaxies lurking behind the Milky Way, particularly in regions aligned with the inferred Great Attractor direction. One of the most important outcomes of infrared surveys was the identification of massive galaxy clusters in the Norma region. These clusters contained hundreds of galaxies bound together by gravity, embedded in large reservoirs of dark matter. X-ray observations confirmed their mass by detecting hot intracluster gas heated to tens of millions of Kelvin. The gravitational influence of these systems was substantial, but still not sufficient on its own to explain the full extent of the observed cosmic flow. This led to a refined understanding. The Great Attractor was not a single hidden object concealed behind dust. It was a region, a convergence of multiple mass concentrations embedded within the cosmic web. The zone of avoidance had hidden not a solitary structure, but a complex intersection of filaments and clusters whose combined gravitational pull-shaped motion across tens of megaparsecs. The process of uncovering this structure was incremental and careful. Astronomers compared velocity maps with infrared galaxy distributions and X-ray cluster catalogs. Each dataset filled in part of the picture. None alone provided a complete explanation. Together, they revealed that the Milky Way sits in front of a particularly dense segment of the nearby universe, obscuring a major node in the local large-scale structure. This realization also clarified why earlier attempts to explain cosmic flows using visible galaxies failed. Optical surveys underestimated mass in the obscured regions. The gravitational influence was real, but the light tracing it was incomplete. Motion had pointed the way long before imaging caught up. Carl Sagan often emphasized that our position in the universe shapes what we can know. Observing from inside a galaxy imposes constraints that observers in intergalactic space would not face. The zone of avoidance is a direct example. It is not a feature of the universe itself, but a feature of our vantage point within it. As observational techniques improved, astronomers learned to compensate. Combining radio, infrared, and X-ray data allowed more accurate mass estimates. Numerical simulations incorporating these mass distributions reproduced observed velocity fields more successfully. The hidden region behind the Milky Way emerged not as an anomaly, but as an expected consequence of hierarchical structure formation. Still, significant uncertainties remain. Even today, some regions behind the densest dust clouds are poorly mapped. Infrared observations reduce extinction but do not eliminate it entirely. Radio surveys are sensitive primarily to gas-rich galaxies and may miss gas-poor systems. X-ray observations detect only the hottest, most massive clusters. Each method has strengths and blind spots. What remains clear is that the most influential nearby gravitational region was hidden not because it was exotic, but because it lay behind our own galaxy. The Milky Way, in this context, acts as both home and obstacle. It provides the platform from which we observe, while simultaneously limiting our line of sight. This situation carries an important methodological lesson. In cosmology, absence of evidence cannot be treated as evidence of absence when observational barriers exist. The zone of avoidance taught astronomers to distrust empty maps when those maps align suspiciously with known limitations of instrumentation. The Great Attractor is no longer an unseen monster lurking in darkness. It is a partially revealed region whose influence was measured long before its contents were catalogued. Gravity announced its presence through motion, Light followed later in wavelengths capable of slipping past the dust of our own galaxy. And yet even as the curtain is pulled back, the view remains incomplete. Because when one hidden region is revealed to be part of a larger structure, attention naturally shifts outward toward how that structure connects to even broader flows beyond it, extending deeper into the cosmic web. Part 5. Is the Great Attractor a single object or something far stranger? Are we being pulled toward one colossal object hidden in space, or toward something far more extended, woven into the fabric of the universe itself? This question marked a turning point in how astronomers understood the Great Attractor, because the accumulating evidence began to resist any explanation. Built around a single, isolated structure, early discussions naturally gravitated toward the idea of one dominant mass. This was a familiar pattern in astronomy. Stars orbit stars, planets orbit stars, galaxies orbit within clusters. It felt reasonable to imagine a single gravitational heavyweight pulling nearby systems inward. But as measurements improved, this interpretation became increasingly difficult to defend. The first challenge came from scale. Velocity data showed that the influence attributed to the Great Attractor extended across regions more than 150 million light-years wide. No known galaxy cluster, even the most massive ones observed, possessed enough mass concentrated in a single location to generate coherent motion over such distances. To explain the observed flows, the mass would need to rival or exceed 10 to the power of 16 solar masses, spread across a wide volume rather than confined to a compact core. Astronomers then turned to X-ray observations to probe the deepest gravitational wells. Hot gas trapped in clusters emits X-rays, and its temperature directly reflects the depth of the gravitational potential, holding it in place. Observations from NASA and European Space Agency satellites revealed multiple massive clusters in the region associated with the Great Attractor, including those near the Norma cluster. Each cluster contained enormous mass, but none alone could account for the total gravitational pull inferred from galaxy motions. This mismatch forced a re-evaluation. Instead of asking where the Great Attractor is, astronomers began asking what it actually represents. The answer that emerged was less visually satisfying, but more consistent with data. The Great Attractor is not a single object. It is a region, a dense knot within the cosmic web, where multiple clusters, groups, and filaments intersect embedded in a dominant concentration of dark matter. Dark matter plays a central role here. Visible galaxies trace only a fraction of total mass. On large scales, dark matter outweighs ordinary matter by roughly a factor of 5. It does not emit or absorb light, but its gravitational influence shapes the motion of galaxies and gas. Computer simulations, calibrated with cosmic microwave background data, show that dark matter naturally forms extended filaments and nodes. These nodes act as gravitational anchors for entire regions of the universe. When astronomers compared velocity flow maps with simulations, the resemblance was striking. The Great Attractor region matched the profile of a major dark matter node rather than a compact mass. Galaxies streamed toward it, along filaments slowing as they approached, much like matter falling into a broad valley rather than a deep pit. Infrared surveys added further clarity. By reducing the effects of Milky Way dust, these surveys revealed a complex network of galaxies behind the zone of avoidance. The distribution was uneven, with several dense clusters embedded within a larger overdense region. This distribution aligned closely with where velocity flows converged. The pull was not coming from one direction alone, but from an extended area whose combined mass dominated the local gravitational field. This picture resolved several lingering inconsistencies. If the Great Attractor were a single object, its gravitational influence would decrease rapidly with distance. Yet observations showed gradual acceleration over vast regions. An extended mass distribution naturally produces such behavior. Gravity remains significant across larger distances when mass is spread rather than concentrated. The story behind this realization reflects the cautious nature of scientific progress. Astronomers did not abandon the single object idea abruptly. They tested it repeatedly against new data. Each new survey chipped away at its plausibility. Only when alternative models consistently matched observations better did the community shift toward the regional interpretation. Carl Sagan often emphasized that understanding comes from assembling many modest truths rather than embracing a single dramatic claim. The Great Attractor exemplifies this approach. No single observation revealed its nature. Instead, galaxy velocities, infrared counts, X-ray gas temperatures, and numerical simulations converged on the same conclusion. Mass estimates reinforced this view. When astronomers summed the mass of visible galaxies in the region, they fell short by a large margin. When dark matter inferred from gravitational effects was included, the numbers aligned. The total mass exceeded that of the Milky Way by tens of thousands of times, not concentrated in one place, but distributed across clusters and filaments. This distribution explains why the Great Attractor remained elusive for so long. A single bright object would have been detected earlier, even behind dust. A diffuse region, however, can remain hidden if its light is spread thinly and obscured by foreground material. Gravity, unlike light, does not fade with obscuration. It announces presence through motion, regardless of visibility. Another line of evidence came from gravitational lensing studies. Although challenging in obscured regions, weak lensing measurements in nearby unobscured areas showed subtle distortions in background galaxy shapes, consistent with large-scale mass concentrations. These distortions aligned with the inferred location of the Great Attractor region, offering independent support for a distributed mass model. By the time these findings were assembled, the question had shifted. The issue was no longer whether the Great Attractor was singular. It was how such regions fit into the broader architecture of the universe. The answer pointed toward superclusters, the largest coherent structures known, composed of clusters, groups, and filaments bound loosely by gravity. The Great Attractor appeared to be one prominent node within a supercluster scale structure. Its influence extended outward, overlapping with other mass concentrations and contributing to complex velocity patterns. This interconnectedness meant that no clean boundary could be drawn. The Great Attractor was not an island. It was part of a continental mass distribution. This realization also reframed earlier measurements. Peculiar velocities that once seemed puzzling now made sense as responses to overlapping gravitational pulls from multiple directions. The observed flow was the vector sum of influences from several massive regions, with the Great Attractor dominating locally, but not acting alone. The scientific restraint in this conclusion is worth noting. Astronomers did not replace one simple picture with another equally simple one. They accepted complexity. The universe on large scales is not organized around singular centers, but around networks of mass that shape motion collectively. From this perspective, the Great Attractor becomes less mysterious and more informative. It demonstrates how dark matter sculpts the universe in ways light cannot fully reveal. It shows that gravitational influence does not require a dramatic focal point. It requires persistence, scale, and accumulation over cosmic time. As this picture became clearer, an additional consequence came into view. If the Great Attractor belongs to a larger structure, then it cannot be stationary. Its mass, immense as it is, must respond to even broader distributions beyond it. Seen this way, the picture expands outward toward larger patterns of motion and structure that lie beyond the local supercluster. Once gravity is considered in terms of extended regions, rather than isolated centers, the focus shifts. The Great Attractor no longer appears as an endpoint, but as part of a continuing flow, raising the possibility that its motion is itself shaped by an even larger arrangement of matter. Part 6. How much of this pull comes from matter that emits no light at all? What if the dominant force guiding the motion of our galaxy comes not from stars or galaxies we can observe, but from matter that never shines, never reflects light, and never announces its presence directly? This possibility is not speculative. It is a conclusion reached slowly through decades of measurements, showing that visible matter alone cannot account for the way galaxies move. The question first gained urgency long before the Great Attractor entered astronomical language. In the 1970s, Vera Rubin and her collaborators measured how stars orbit within spiral galaxies. They expected stars farther from the center to move more slowly following the distribution of visible mass. Instead, they found flat rotation curves. Stars at large radii moved just as fast as those closer in. Rubin summarized the implication with careful restraint, noting that we know far less than we see. The mass governing motion was largely invisible. That lesson did not remain confined to individual galaxies. As astronomers expanded their view to clusters and superclusters, the same discrepancy appeared again and again. The velocities of galaxies within clusters required far more mass than stars and gas could provide. The gravitational pull shaping large-scale flows demanded an even larger unseen component. When velocity maps of the local universe were compared with distributions of visible galaxies, the mismatch became striking. Regions that exerted strong gravitational influence did not always correspond to regions rich in light. Conversely, some luminous regions played only a minor role in shaping motion. This pattern suggested that light traces only a fraction of the true mass distribution. Dark matter emerged as the simplest explanation, consistent with all available data. It interacts gravitationally, but does not emit, absorb, or scatter electromagnetic radiation in any measurable way. Its presence must be inferred from motion lensing and structure formation. In simulations calibrated with cosmic microwave background data from missions such as Planck dark matter forms the scaffolding of the universe, while ordinary matter settles into its gravitational wells. In the context of the Great Attractor, this insight proved decisive. Visible galaxies and clusters, identified in infrared and X-ray surveys, contributed significant mass, but still fell short of explaining the observed cosmic flow. When dark matter was included distributed across filaments and nodes, the numbers aligned. The gravitational pull required to move entire clusters across tens of megaparsecs emerged naturally. Mapping dark matter directly is impossible with light, but its distribution can be inferred through gravitational lensing. Even weak lensing, which produces subtle distortions in the shapes of background galaxies, reveals mass concentrations independent of luminosity. Surveys, supported by NASA and the European Space Agency, showed that mass maps derived from lensing often diverged from light-based maps. The strongest lensing signals did not always coincide with the brightest regions. This discrepancy matters for understanding cosmic flows. If motion responds to total mass rather than visible mass, then velocity fields should correlate more closely with dark matter maps than with galaxy counts alone. This expectation was tested using numerical reconstructions of the local universe. The results were consistent. Velocity vectors aligned with predicted dark matter overdensities, including those associated with the Great Attractor region. Another line of evidence came from simulations of structure growth. Starting from tiny density fluctuations measured in the cosmic microwave background, simulations showed dark matter collapsing, first forming filaments and nodes. Ordinary matter follows later, cooling and forming stars within these structures. In this picture, light is a latecomer. Gravity acts long before stars illuminate the scene. This sequence explains why the Great Attractor appeared invisible for so long. Its gravitational influence was established early, but much of its mass never formed luminous galaxies. The region is dominated by dark matter, with visible clusters marking only the densest peaks. Motion revealed the underlying structure before light could. The role of dark matter also clarifies why the pull is broad rather than focused. A single luminous object would produce a steep gravitational gradient. An extended dark matter concentration produces a wide basin, guiding motion gently but persistently over enormous distances. This matches observations of gradual acceleration and coherent flow. Importantly, dark matter does not act alone. Ordinary matter still contributes. Hot gas in clusters detected through X-ray emission accounts for a significant fraction of baryonic mass. But even when gas and stars are combined, they typically represent less than 20% of the total mass required. The remainder must be dark. The scientific process behind this conclusion is cumulative. No single experiment measured dark matter directly. Instead, multiple independent methods converged. Galaxy rotation curves, cluster dynamics, gravitational lensing, cosmic microwave background, anisotropies, and large-scale simulations all pointed in the same direction. The Great Attractor is simply one of the clearest nearby examples where these lines intersect. Vera Rubin's work provided a critical conceptual bridge. By demonstrating that light does not reliably trace mass even within galaxies, she prepared astronomers to accept the same principle at much larger scales. When galaxy motions refused to match visible distributions, the lesson was already in place. This understanding reshaped how cosmologists interpret maps of the universe. A map of light is no longer treated as a map of gravity. Instead, it is viewed as an incomplete overlay on a much larger, darker structure. Motion, not brightness, becomes the more faithful guide. The implications extend beyond the Great Attractor. If most gravitational influence comes from dark matter, then every large-scale flow reflects the hidden architecture of the universe. Cosmic expansion provides the backdrop, but dark matter determines how that expansion is locally shaped, slowed, or redirected. Despite its importance, dark matter remains unidentified at the particle level. Experiments on Earth have yet to detect it directly. This uncertainty does not weaken its role in cosmology. On the contrary, its gravitational effects are measured with extraordinary consistency across scales ranging from galaxies to the observable universe. In the Great Attractor region, dark matter transforms what once seemed like an invisible monster into a predictable outcome of structure formation. The pull moving our galaxy is not mysterious in mechanism. It follows the same gravitational rules that govern orbits and clusters. What is unusual is only our position observing from within a dusty galaxy that obscured the view. With this picture in place, one pattern becomes difficult to overlook. The motion of the Milky Way is not governed primarily by what is visible. It responds to mass that far exceeds what light alone can trace. Most of the gravitational landscape remains dark, yet it continues to shape motion steadily across cosmic time. When dark matter is taken as the dominant influence, the view widens again. The pull associated with the Great Attractor no longer appears confined to a single region, but reflects dark matter spread across a much larger volume. That distribution, in turn, fits into an even broader pattern of mass and motion, extending beyond what current maps have been able to fully resolve. Part 7. Is the Great Attractor even the final destination? What if the Great Attractor is not the end of the journey at all, but only a waypoint itself, moving within an even larger current that carries entire superclusters across the universe? This possibility emerged not from speculation, but from a careful re-examination of galaxy motions. Once astronomers stopped asking where galaxies are and focused instead on where they are going. For decades, cosmic maps were drawn primarily from redshift surveys. These maps showed where galaxies appeared to be located based on how fast they receded due to cosmic expansion. But redshift alone does not reveal direction of motion through space. It tells us how fast distance changes along our line of sight, not how galaxies drift sideways under gravity. To uncover that information, astronomers had to combine redshift data with precise distance measurements and reconstruct full three-dimensional velocity fields. This task required patience and restraint. Distances are notoriously difficult to measure on cosmic scales. Each method carries uncertainty, and those uncertainties propagate into velocity calculations. Yet by the early 21st century, enough high-quality data had accumulated to attempt something ambitious. Astronomers began mapping not just positions, but flows. Using thousands of galaxy distances derived from well-calibrated indicators, researchers constructed a cosmic flow map of the local universe. The result was revealing. The Great Attractor did not appear as a terminal sink where motion simply ended. Instead, it sat within a larger pattern of converging streams, as though it were itself responding to forces acting on even greater scales. This realization reached a turning point in 2014, when a team led by Richard Brent Tully published an analysis that reframed our cosmic address. By tracing galaxy velocities rather than positions alone, they identified a vast region of space within which matter flows inward toward a common basin. They named this region Laniakea, a word from Hawaiian meaning immeasurable heaven chosen to reflect scale rather than sentiment. Laniakea is not a cluster. It is not a compact object. It is a supercluster scale domain defined by motion. Galaxies inside it share a general flow pattern, while galaxies outside move toward different basins. The Milky Way, along with the Virgo cluster and the Great Attractor region, lies well within this domain. The scale of Laniakea is difficult to grasp. It spans more than 500 million light-years, roughly 160 megaparsecs, and contains on the order of 100,000 galaxies. Its total mass, dominated by dark matter, far exceeds anything associated with individual clusters. In this context, the Great Attractor becomes one prominent feature within a much larger gravitational landscape. The evidence for this structure came not from a single observation, but from the coherence of motion across enormous distances. When velocity vectors were plotted, they did not terminate at the Great Attractor. They continued beyond it, bending and aligning with broader flows. The Great Attractor appeared as a local convergence, nested within a deeper basin that defined Laniakea itself. This nested structure resolves several puzzles left by earlier interpretations. If the Great Attractor were the final destination, velocities should diminish sharply near its center. Instead, motion remained structured and directional beyond it. By recognizing Laniakea as the larger domain, astronomers accounted for these extended flows naturally. The method behind this discovery deserves attention. Rather than drawing boundaries based on galaxy density alone, astronomers defined superclusters by flow lines. A boundary was placed where motion diverged, not where light faded. This approach emphasized dynamics over appearance and produced a more physically meaningful classification. NASA and European Space Agency data played an essential role. Observations of the cosmic microwave background provided the reference frame needed to define peculiar velocities accurately. Infrared surveys filled in obscured regions. X-ray observations identified massive clusters anchoring flows. Each dataset contributed a piece, but none dominated. The strength of the conclusion lay in their agreement. In this framework, Laniakea is not static. It is part of an even larger network of flows connecting superclusters across the cosmic web. Beyond its boundaries lie other basins, separated by regions where gravitational influence balances. Matter streams from voids toward filaments, from filaments toward nodes, and from nodes toward deeper concentrations. The universe appears organized not as isolated structures, but as a hierarchy of motion. This perspective alters how the Great Attractor is understood. It is no longer a mysterious endpoint pulling galaxies toward it from all directions. It is a major node within Laniakea itself, shaped by mass distributions on even larger scales. Its pull is real, but not absolute. The story behind this shift illustrates the discipline of cosmology. Astronomers did not discard the Great Attractor concept. They refined it, embedding it within a broader context, supported by data. The name remained useful, but its meaning evolved from object to region, and from region to component of a supercluster scale flow. Carl Sagan often emphasized that our understanding of the universe grows by widening perspective. Each increase in scale reveals patterns invisible before. Laniakea represents such an expansion of view. It does not negate earlier findings. It incorporates them, placing local motion within a larger map of gravitational influence. Importantly, none of this implies a simple destination where matter will ultimately collect. Cosmic expansion continues to act on the largest scales, stretching space and limiting how much structure can grow. Superclusters like Laniakea are not gravitationally bound in the same way clusters are. Over immense timescales, expansion will dominate, and these flows will slow. But in the present universe, gravity still sculpts motion across hundreds of millions of light years. The Milky Way's velocity, once attributed to a single hidden attractor, is now understood as the sum of influences from nested structures. Each layer adds coherence without demanding a central anchor. The discovery of Laniakea also highlights the power of motion as a probe of mass. Light reveals where stars are. Motion reveals where gravity acts. When the two are combined, the underlying structure of the universe becomes clearer, even when much of its mass remains invisible. The Great Attractor is not the final destination. It is a landmark along a much longer route, defined by cosmic flows. Our galaxy is carried within a supercluster-scale current that extends far beyond what earlier maps could show. When Laniakea is understood in terms of flow rather than fixed boundaries, its place in the universe expands further. It no longer appears as a self-contained structure, but as part of a much larger arrangement where superclusters outline the largest patterns the universe permits. These patterns are linked by long filaments and separated by immense voids together, shaping motion on the widest scales yet observed. Part 8. Could this enormous pull ever threaten the Milky Way or Earth? If our entire galaxy is moving through space under the influence of immense gravitational forces, should that motion be a cause for concern for the Milky Way or for system Earth itself? The question feels natural because motion on cosmic scales is often imagined as violent or disruptive. Yet when examined carefully, the data tell a far calmer, more precise story, one defined not by sudden danger, but by time measured in billions of years. The Milky Way is moving at several hundred kilometers per second, relative to the cosmic microwave background. This number sounds dramatic when stated on human terms, but speed alone has little meaning without context. In space, what matters is not absolute velocity, but acceleration, proximity, and timescale. A galaxy can travel vast distances smoothly if forces change slowly and gradients are shallow. To understand whether the Great Attractor or larger cosmic flows pose any threat, astronomers begin by comparing timescales. The characteristic timescale of large-scale cosmic motion is set by the growth of structure in the universe. That growth unfolds over billions of years. The flows that carry galaxies toward massive regions are steady and gradual, not abrupt. The Milky Way has been responding to these gravitational patterns since long before the Sun formed. One useful comparison comes from within our own galaxy. The Sun orbits the center of the Milky Way at a speed of about 220 kilometers per second, completing one orbit roughly every 230 million years. This motion does not threaten the solar system. It is stable because the gravitational field changes slowly over the scale of the orbit. The same principle applies on larger scales. The gravitational pull associated with the Great Attractor and the Laniakea supercluster changes extremely gradually across space. There is no sharp boundary, no sudden increase in force. The Milky Way is not falling toward a cliff. It is moving along a broad gradient, shaped by mass distributed over tens to hundreds of megaparsecs. Another concern, often raised, is the possibility of galaxy collisions. Collisions do occur in the universe, but they are driven by local dynamics, not by supercluster-scale flows. The most significant future interaction for the Milky Way is its encounter with the Andromeda Galaxy, predicted to begin several billion years from now. This event is governed by the mutual gravity of two neighboring galaxies, not by the Great Attractor or any larger structure. Even during galaxy mergers, stars rarely collide directly. The distances between stars are enormous compared to their sizes. When galaxies merge, their shapes change, gas clouds interact, and star formation may increase, but individual planetary systems are largely unaffected. This understanding comes from detailed simulations and observations of interacting galaxies conducted by NASA and the European Space Agency. On the scale of Earth, the influence of cosmic flows is negligible. The gravitational acceleration produced by the Great Attractor at our location is vastly smaller than that exerted by the Milky Way itself, which, in turn, is far smaller than the gravitational pull of the Sun, and smaller still than that of Earth. These influences are nested hierarchically with local forces dominating completely. To quantify this hierarchy without equations, consider how gravity weakens with distance. The Great Attractor lies tens of megaparsecs away. Even with its enormous mass, the resulting gravitational tug at our position is extraordinarily gentle. It alters the velocity of the Milky Way by tiny amounts over hundreds of millions of years. By contrast, the Sun's gravity shapes Earth's orbit continuously and precisely, overwhelming any external effect. Observations support this picture. Geological records on Earth show no correlation with cosmic motion. Stellar populations within the Milky Way show no signs of disturbance associated with large-scale flows. The structure of the galaxy remains stable on timescales comparable to its age. If cosmic pulls posed a threat, evidence would appear somewhere in these systems. Astronomers also examine the stability of galaxy clusters embedded in superclusters. These clusters remain bound over long periods, even as they participate in larger flows. This tells us that local gravitational binding is robust against supercluster-scale motion. The same principle applies to galaxies and planetary systems. The language of being dragged can be misleading. The Milky Way is not being pulled against resistance. It is moving through expanding space, responding to the distribution of mass around it. There is no friction, no stress, no internal strain imposed on the galaxy by this motion. All parts of the Milky Way share nearly the same large-scale velocity, preserving internal coherence. This shared motion is crucial. If different parts of the galaxy were accelerated differently, tidal effects could arise. But the gravitational field from distant mass concentrations is nearly uniform across the size of the Milky Way. The galaxy moves as a whole, not as a collection of independently tugged components. Computer simulations reinforce this conclusion. When large-scale flows are included in cosmological models, galaxies remain structurally intact over cosmic time. They form, evolve, and interact locally, while their collective motion through space remains smooth. No simulation predicts disruption from supercluster-scale attraction alone. The history of the universe provides further reassurance. Large-scale flows have existed since early times. Galaxies have been moving within them for more than 10 billion years. During that time, stars formed, planetary systems emerged, and life appeared on at least one planet. The conditions that allow complex structures to persist are compatible with these motions. Carl Sagan often reminded audiences that scale changes perspective. Events that seem dramatic on human scales can be inconsequential on cosmic ones. The movement of galaxies across hundreds of millions of light-years is slow when measured against the lifespan of stars and galaxies themselves. The universe evolves patiently. Another source of confusion comes from conflating expansion with motion. Cosmic expansion increases distances between unbound structures, but it does not tear apart bound systems. The Milky Way, the local group, and even clusters remain bound because their internal gravity exceeds the effect of expansion. Supercluster-scale flows operate in a regime where gravity and expansion coexist without conflict. When astronomers communicate risk, they rely on orders of magnitude. On that scale, the influence of the Great Attractor on Earth ranks effectively at zero. There is no credible mechanism by which this pull could destabilize the solar system, alter Earth's orbit, or affect life. The scientific value of studying these motions lies elsewhere. They reveal how mass is distributed, how dark matter shapes structure, and how the universe organizes itself on the largest scales. They are diagnostic tools, not harbingers of danger. Across observation, simulation, and theory, one feature of these motions remains consistent. The gravitational pull influencing our galaxy is real and measurable, revealing important features of how mass is arranged across the universe. Yet it operates over distances and timescales so immense that it poses no direct influence on stars, planets, or life. Seen at that scale, the focus shifts away from immediate consequence and towards structure. These vast flows are not significant because they threaten local systems, but because they expose an underlying framework that organizes motion across the largest scales the universe permits. Part 9. What the Great Attractor reveals about the skeleton of the universe. What if the motion of galaxies does not originate from isolated forces, but from an underlying framework that guides everything long before stars ever formed? The time astronomers placed the Great Attractor within the proper context, this question became unavoidable, because the evidence no longer pointed to a single region acting alone, but to a vast interconnected structure shaping motion across the universe. The idea that matter in the universe forms a web did not emerge from philosophy or metaphor. It emerged from data. As galaxy surveys expanded in depth and scope during the late 20th century, astronomers noticed that galaxies were not scattered randomly. Instead, they arranged themselves into elongated chains, flattened walls, and dense intersections, separated by enormous regions containing very few galaxies. This pattern appeared consistently, regardless of survey method or wavelength. When redshift surveys, such as the CFA Redshift Survey and later the Sloan Digital Sky Survey, mapped millions of galaxies, the large-scale structure became unmistakable. Galaxies traced filaments tens to hundreds of megaparsecs long. Clusters marked intersections where filaments crossed. Vast voids stretched between them, sometimes spanning more than 100 megaparsecs. This arrangement became known as the cosmic web. The importance of this structure lies not in appearance alone, but in dynamics. Gravity does not act uniformly across space. It follows mass. In the cosmic web, mass is concentrated in filaments and nodes, with voids containing far less matter. As a result, galaxies do not simply recede from one another due to expansion. They also stream along filaments, fall toward nodes, and avoid voids. The Great Attractor fits precisely into this picture. Once velocity flow maps were compared with galaxy distributions and dark matter simulations, it became clear that the Great Attractor corresponds to a major node within the local cosmic web. It is a region where multiple filaments converge, producing a deep gravitational basin that shapes motion over vast distances. This realization resolves a long-standing puzzle. Earlier interpretations struggled to explain why the Great Attractor's influence extended so broadly and smoothly. Within the cosmic web framework, this behavior is expected. Filaments act as channels that guide matter toward dense regions. Galaxies entering these channels experience coherent acceleration, producing the large-scale flows observed in velocity surveys. Dark matter plays a central role in this structure. Simulations beginning with tiny density variations measured in the cosmic microwave background show dark matter collapsing first. It forms the initial skeleton of the universe. Ordinary matter then follows cooling and forming galaxies along this framework. The web is therefore not traced by galaxies because galaxies created it, but because galaxies formed within it. NASA and European Space Agency observations of weak gravitational lensing provided a crucial confirmation. Lensing maps revealed mass concentrations aligned with filaments, even where few galaxies were visible. These mass maps matched predictions from simulations and aligned with observed velocity flows. The cosmic web was no longer an abstract model. It was directly observed through its gravitational effects. Within this structure, voids are as important as filaments. Voids are regions of low density that expand more rapidly than average. Matter flows out of them toward denser surroundings. This outflow contributes to the motion of galaxies along filaments toward nodes such as the Great Attractor. In this sense, motion is shaped as much by what is absent as by what is present. The Great Attractor does not dominate motion because it is unique. It dominates because it sits at a critical intersection of filaments in our local region of the universe. Its influence is amplified by the combined mass of these filaments and by the continuous inflow of matter from surrounding voids. This framework also explains why velocity maps often appear smoother than galaxy maps. Light traces discrete objects. Gravity traces total mass, including dark matter distributed continuously along filaments. Motion responds to this smooth mass distribution, producing coherent flows even when galaxies appear sparse. The story behind recognizing the cosmic web illustrates the power of combining observation and simulation. Early redshift surveys hinted at structure but lacked scale. Later, surveys confirmed patterns but required interpretation. Simulations then showed how such patterns arise naturally from gravitational evolution in a universe dominated by dark matter. Each step reinforced the others. Carl Sagan often spoke about the importance of pattern recognition in science, the ability to see coherence where earlier views saw noise. The cosmic web exemplifies this process. What once appeared as scattered clusters now appears as a connected system governed by gravity and initial conditions set shortly after the Big Bang. Within this system, the Great Attractor serves as a local demonstration of a universal principle. Motion is not chaotic. It follows structure. Galaxies move the way. Rivers follow terrain guided by gradients established long before their journey began. This understanding has predictive power. By mapping the cosmic web, astronomers can anticipate velocity flows even in regions not yet fully observed. When new surveys probe obscured or distant areas, the results often align with predictions based on web structure. The agreement strengthens confidence in the framework. The cosmic web also places limits on structure growth. Filaments and nodes grow by accretion, but cosmic expansion eventually slows this process. Superclusters are not fully bound objects. They are transitional structures shaped by gravity, but influenced by expansion. The web itself evolves, but within constraints imposed by the universe's overall dynamics. From this perspective, the Great Attractor is not an anomaly. It is an expected outcome of cosmic evolution. Its discovery was surprising, only because the underlying structure was not yet fully recognized when velocity anomalies were first measured. As surveys such as those conducted with the James Webb Space Telescope extend observations to earlier cosmic times, the web is seen in younger form. Filaments appear less pronounced, nodes less massive. Over billions of years, gravity sharpened these features, guiding matter into the patterns observed today. The lesson is cumulative. Individual galaxies do not decide their paths independently. Their motion reflects the distribution of mass on scales far larger than themselves. The Milky Way's journey toward the Great Attractor, and beyond it, within Laniakea, is one thread within a vast network of flows spanning the observable universe. This perspective transforms the original mystery. The question is no longer why our galaxy is moving, or even what is pulling it. The deeper insight lies in recognizing that motion itself reveals the structure of the universe. By following the paths of galaxies, astronomers have traced the invisible framework that organizes matter on the largest scales. Observations consistently show that the Great Attractor is not an isolated anomaly. It is a nearby manifestation of the cosmic web itself, reflecting a universal pattern of mass and motion that extends far beyond our local region. Even so, the structures we currently map may represent only a portion of that larger framework. The cosmic web, as it appears today, is shaped by physical laws and early conditions that still press against the limits of what observation can fully resolve. Part 10. Are there even larger attractors still waiting to be discovered? If one hidden structure was powerful enough to shape the motion of our entire galaxy, how many other influences might still exist beyond the limits of our current calm? Maps quietly guiding motion on scales we have only begun to chart. This question stands at the natural edge of everything uncovered so far, because each expansion of perspective in cosmology has historically revealed that what seemed complete was only partial. The Great Attractor once appeared as an endpoint. Later it became a region within Laniakea. Then, Laniakea itself was recognized as one domain within an even larger cosmic web. At every stage, the pattern repeated. Improved data did not erase earlier discoveries. It placed them inside wider structures governed by the same gravitational rules. This pattern is not accidental. It arises from how the universe grows structure. Tiny density variations, measured in the cosmic microwave background by missions such as Wilkinson Microwave Anisotropy Probe and Planck, provided the initial conditions. Over billions of years, gravity amplified those variations, producing filaments, nodes, and voids on ever larger scales. There is no sharp cutoff where structure abruptly ends. Instead, there is a gradual transition, where gravity competes with cosmic expansion. Current observations suggest that superclusters like Laniakea are among the largest partially coherent structures that gravity can shape in the present universe. They are not fully bound objects, but they do influence motion over hundreds of megaparsecs. Yet even these structures sit within broader patterns of density that extend farther still. Evidence for this comes from large-scale surveys of galaxy clustering. When astronomers analyze correlations in galaxy positions over scales exceeding 1 billion light-years, they detect subtle preferences. These correlations indicate that matter distribution is not entirely random, even at those scales. The amplitudes are small, but they are measurable and consistent with predictions from cosmological models, supported by NASA and European Space Agency observations. Velocity studies hint at similar complexity. While cosmic flows weaken with distance, they do not vanish suddenly. Some surveys have reported bulk motions extending beyond the scales of known superclusters. These measurements remain an area of active research because uncertainties grow rapidly with distance. Still, they serve as reminders that the map is incomplete. Future observations are designed specifically to address these limits. Next-generation galaxy surveys will map tens of millions of galaxies across a large fraction of the observable universe. These surveys aim not only to record positions, but to measure distances with improved precision, enabling better reconstruction of velocity fields. Each improvement in distance accuracy sharpens the ability to detect coherent motion. Gravitational lensing will play a central role. Weak lensing surveys measure mass directly independent of light. By mapping subtle distortions in background galaxies, astronomers can reconstruct dark matter distributions across enormous volumes. These maps already reveal filaments stretching across hundreds of megaparsecs. With greater sensitivity, they may reveal even broader mass gradients shaping motion. The James Webb Space Telescope contributes in a complementary way. By observing the universe at earlier epochs, it allows astronomers to see how large-scale structures assembled over time. If today's superclusters emerged from earlier density patterns, then observing their precursors provides constraints on how large future structures can become. Early observations already show galaxies forming along filaments when the universe was only a few billion years old. Another frontier lies in radio astronomy. Surveys of neutral hydrogen using large radio arrays can trace matter distributions across cosmic time, including regions heavily obscured in optical light. These surveys extend the reach of structure mapping into domains previously inaccessible, reducing blind spots similar to the zone of avoidance that once hid the Great Attractor. All of these efforts serve a common goal. They test whether structures larger than known superclusters exert measurable influence on galaxy motion, or whether cosmic expansion ultimately overwhelms gravity at those scales. The answer is likely subtle rather than dramatic. Gravity does not suddenly stop acting. Its influence tapers, gradually shaped by the universe's expansion history and dark energy. Dark energy introduces another layer of complexity. As the universe expands, dark energy accelerates that expansion, reducing the ability of gravity to form new large-scale bound structures. This sets an upper limit on the size of coherent attractors that can emerge in the current epoch. Structures beyond that limit may influence motion weakly, but they will not collapse into denser systems. This understanding reframes the original unease. The universe may still be pulling us in ways not yet fully mapped, but those pulls are constrained by well-tested physical laws. They are gentle, cumulative, and slow. They reveal structure without threatening stability. The history of the Great Attractor offers a guide. It was not discovered by chance, nor by dramatic observation. It emerged from careful attention to discrepancies between motion and light. Future discoveries will likely follow the same pattern. They will appear first as small mismatches, subtle flows that resist easy explanation, prompting deeper surveys and refined models. Carl Sagan often emphasized that science advances by recognizing how much remains unknown, not as a source of fear, but as a source of motivation. Each hidden structure revealed so far has deepened understanding rather than undermined it. The universe has proven to be orderly, even when complex. As cosmology moves forward, the emphasis will remain on integration. Light-based surveys, mass maps from lensing velocity reconstructions and simulations grounded in early universe physics must all align. When they do, confidence grows that the picture is converging toward completeness, even if absolute completeness remains unattainable. The Great Attractor began as a mystery tied to our own motion. It ended as a lesson about the universe's architecture. Motion traces mass. Mass traces structure. Structure reflects initial conditions and physical laws that operate consistently across vast scales. There may indeed be larger attractors, broader basins of influence beyond Laniakea woven into the cosmic web at scales we are only beginning to measure. If they exist, they will not announce themselves loudly. They will be inferred patiently through careful comparison of prediction and observation. As this journey concludes, one thing remains clear. The universe is not finished revealing itself. Each generation of instruments extends the map, not by overturning what came before, but by placing it within a wider frame. Thank you for spending this long exploration here, following the evidence from the motion of our own galaxy to the largest structures we can currently trace. Wherever you are listening from and whatever hour has carried you to this point, wishing you a peaceful rest and a very good night. Good night.